Now our question is 716. The steel rod has a radius of 30 millimeters. If it is subjected to a shear of V 22.5 kilonewtons, determine the maximum shear stress. Okay, so question is simple and straightforward, in fact. So obviously we have a symmetric cross section, and neutral axis is the axis of the shaft. In fact, we are asked for the maximum shear stress. So let me remind you the shear stress formula. Tau is equal to V multiplied by Q divided by bending moment of inertia and multiplied by the thickness, the width of the cross section at that location. In fact, this tells us that the shear stress is maximum because the shear force is constant, bending moment of inertia is constant, and in fact shear stress is maximum when ratio of Q to T is maximum. Certainly the moment is maximum on the neutral axis. So the shear stress is maximum. If we draw the shear stress, it's going to be like this. So this is the magnitude of the shear stress. So it is maximum here. Okay, so basically this means that we need to calculate the Q at the center according to the neutral axis, which means that certainly we will consider this area, and it is geometric center is located at, so let's say that this is Y bar and this area is A bar. So Y bar is known to be 4/3 R divided by P. So R is the radius of the circle. Okay, now let's calculate the values. In fact, so Q is equal to Y bar multiplied by A bar. Y bar is equal to 4/3 R divided by P from geometry. If you put the values, it is 4. Radius is given as 30 millimeters. It is 0.03 meters. Divided by 3P. So the value that we are going to have is 0.0127 meters. So this is the distance from the neutral axis, in fact. Now we can calculate the A bar. So A bar is equal to P R square divided by 2, because we only consider half of the circle, and if you put the values, what you are going to get is 1.413 meters square. Now we can calculate the Q value. So let me write the Q again here. It is Y bar multiplied by A bar, and in fact if you put the values, what you are going to get is 1.8 10 to the power minus 5 meter to the cube. In fact, I need to correct this value. It is 1.413. Let me write it again. So A bar is 1.413 10 to the power minus 3 meter to the square. And then you can easily calculate the moment of the area, first moment of the area. It is the centroid of the area multiplied by the area itself. So this is 1.8 10 to the power minus 5 meter to the cube. Now we need to calculate the bending moment of inertia with respect to neutral axis. So bending moment of inertia with respect to the neutral axis for a circular cross section is P r to the power 4 divided by 4. So it is P 0.0 to the power 4 divided by 4. And the value that we are going to get is 6.361 10 to the power minus 7 meter to the power 4. Now we can calculate the maximum shear stress. Maximum shear stress for this cross section is shear force multiplied by first moment of the area multiplied by divided by bending moment of inertia with respect to the neutral axis multiplied by the thickness. Thickness on the neutral axis is 2r. If you put the values, it is 22.5 10 to the power 3 newtons. So first moment of inertia is 1.8 10 to the power minus 5 divided by 6.361 10 to the power minus 7 multiplied by 0.06. So what you are going to get is 10.61 megapascals. So this is the answer of the question. Okay, our next question is 719. If the wide flange beam is subjected to a shear of 30 kilonewtons, determine the shear force resisted by the web of the beam. Set W is equal to 200 millimeters. So we have an I-beam because the width of the lower flange is set to 200 millimeters, and therefore it is equal to the upper flange. We are asked for the force resisted by the web. So the web is located from A to B. So this vertical part is the web and the horizontal part is the flange. The thickness of the web is given. It is 25 millimeters, and in fact the thicknesses of the flanges are 30 millimeters. And the distance between the two flanges is given as 250 millimeters. So let's begin by defining the variables first. So we have an I-beam. This is our I-beam. Let's say that this distance is W. This dimension. And it is symmetric, therefore we don't need to calculate the location of the neutral axis, so it is just at the geometric center. So it is just at the center. Okay, so the distance, the dimension between the distance between the two flanges is, let's say, h, and the thickness of each flange is, let's say, T1, and the web is T2. In fact, in this case, h is 0.25 meters, w is 0.2 meters, T1 is 0.03 meters, and T2 is 0.025 meters. We are also given the shear force V, that is 30 kilonewtons. Now, first thing that I need to do is to calculate the bending moment of inertia for this cross section. With respect to the neutral axis, of course. Now, what I can do is, first I can assume that there is a one big box, rectangular box, calculate its moment of inertia, and then subtract these two rectangular parts with respect to the centroid. This is one way of calculating the moment of inertia, bending moment of inertia. And the second approach is dividing this cross section into subsections and calculating the bending moment of inertia. In fact, one choice is the flange and one web and two flanges independently. This is what I'm going to do, but I will write both equations for you. They are both identical, in fact. First, I will calculate the moment of inertia of the flange. So it is 1 over 12. The thickness, the width is T2 multiplied by h cube. This is h plus I have two flanges here, so it is 1 over 12. The width is W and the height is T1, so T1 cube. Then I will shift it to the neutral axis, so the area is W multiplied by T1, and the distance of each flange to the centroid is h divided by 2 plus T1 divided by 2. This is one way of calculating the moment of inertia. In fact, it's identical. I will show the other way. Now what I'm going to do is, first I will assume that this I-beam as a one big rectangular box. Then I will subtract the moment of inertia of these empty regions. So 1 over 12, width is W, it is, the height is h plus 2T1, and the cube of it minus 2. Now I will consider this small part, so in fact again it is 1 over 12. The width of this region is W divided by 2 divided by T2 divided by 2, so it is W minus T2 divided by 2. This is the width, and the height of this region is h, so this is h cube. Or if I write it in a more simplified way, it is 1 over 12 W h plus 2T1 cube minus 1 over 12 W minus T2 h cube. So this expression and this expression, these expressions are identical. They will give me the same value. And the result, the numerical value that we are going to have is 2.686 10 to the power minus 4 meter to the power 4. Now we will calculate the first moment of the area for an arbitrary location above the neutral axis. So for this purpose, so I put a reference coordinate system on the neutral axis. So let's say that this is y. In fact, now I will consider the moment of the area above this location. as you see, I have an area which is constant, so it stays there because I'm interested in flange. So basically from here to here I don't need to calculate the variation of the stress in this region, because what is asked to me is the force carried by the web. So I don't need to calculate the variation in the flange, in fact. Okay, so this is the area that I will consider. Now I will write first moment of the area as a function of y. Of course, first I will write the moment of the first moment of the flange. So in fact it is area multiplied by the centroid of it, so it is W multiplied by T1 multiplied by H plus T1 divided by 2. Now I will consider the moment of this area. Now it has a thickness of T2, okay, and its width is H divided by 2 minus y. So the area is H divided by 2 minus y multiplied by T2. Now the centroid. In fact, the centroid is located at H divided by 2 minus y divided by 2 plus y. So this is the expression for the first moment of the area for this for the region above the neutral axis. So if you put the values into their places, what we are going to get is it is 1.035 10 to the power minus 3 minus 0.0125 y square, and the unit is meter to the power cube. Okay, now we have found the moment, first moment of the area. Now we can calculate the shear stress distribution. In fact, so the shear stress distribution is tau as a function of y. It is the shear force multiplied by first moment of inertia Q divided by bending moment of inertia, first moment of the area Q and bending moment of inertia, and multiplied by the thickness of the web, because we are asked for the force carried by the web. So it is T2. Let's put the values into their places. V is 30 10 to the power 3 multiplied by 1.035 10 to the power minus 3 minus 0.0125 y square again, let me repeat it. It is 0.35 multiplied by 10 to the power minus 3 minus 0.0125 multiplied by y square. So square of the y divided by bending moment of inertia, and bending moment of inertia is 2.686 10 to the power minus 4 multiplied by thickness, and thickness is T2. T2 has a value of 0.025. Sorry, this is 0.025. Okay, so this is the shear stress distribution. Now the value we have, the expression is then 4.624 10 to the power 6 minus 5.583 10 to the power 7 y square. So this is the value that we have. Now we are asked for the shear force carried by the web. Now what we are going to do is we will integrate it. We will integrate the shear. So let's say that we we will integrate the stress in the web. Flange is located from minus h divided by to h divided by 2, and the stress is Ty. In fact, we have an infinite small area. The area is T2 multiplied by dy. So basically I take a very small unit area here, dA, let's say, and this dA is equal to T2 multiplied by dy. Okay, so if you do the integration and put the values, what you are going to get as a result is 27,085.4 newtons. This is the answer of the problem. Now our problem is 722. Determine the shear stress at point B on the web of the cantilevered strut at section AA. So we have a beam which is fixed to the wall, which is anchored. There are 2 point loads which are 2 kilonewtons and 4 kilonewtons. The distance to the wall is given, and the beam has a cross section which is like reversed. In fact, we are asked for the shear stress on the web of the cross section at section AA, so at point B. Okay, so the dimensions of the cross section is already given. So first thing that we need to do is we need to draw the shear force distribution. We can do it in different ways. In fact, first let me draw the free body diagram of the system, of the beam. This is our beam. We are given 2 forces. Let's say that this is F2 and this is F1. So F1 is equal to 2 kilonewtons and F2 is equal to 4 kilonewtons. We have the fixed support which is anchored. We don't have any horizontal component of the force, so therefore I will only have reaction in the vertical direction at the support, and this is what I'm going to do, what I'm going to draw. Then I have the moment at A. I draw the moment in order to be complete. Now I know that this system has to be static equilibrium. I will begin to draw the shear for distribution either from the left hand side or from the right hand side, but in fact I prefer to draw it from the right hand side in order to show how to find the shear force distribution. Therefore I will only calculate the force at A. So sum of the forces has to be equal to 0. I only have forces in vertical direction, therefore FA is equal to F1 plus F2, which makes 6 kilonewtons. I will not calculate the moments. In fact, you can do it. So I begin to cut the structure from the right hand side. I have FA here, I have MA, now I have the shear force here. Let's say that this is V1, and then I have the moment, bending moment M1. So I made a cut somewhere here. This is my first cut and this will be my second cut. Okay, so from here I can find the V1. V1 is equal to FA, and that's equal to 6 kilonewtons. Now I will make a second cut between F1 and F2, between two forces, 2 point loads. So I have the FA, I have the bending moment, support reaction moment at A. Now I have F1, I have here V2, and I have M2. In fact, I can calculate the V2. V2 is equal to FA minus F1. So it is 4 kilonewtons. Now I can draw the shear force distribution. As a function of the coordinate. So this is my V. First it is constant, then it decreases, then so this is 6 kilonewtons and this point is 4. In fact, this is the location where I have the force 1, which has the magnitude of 2 kilonewtons. So my cross section A is, so basically this is this point is 0.5, so if this is in meters, and this is 0.8, this point is 0.8, and I'm interested in, so we are asked for the stress at this location, and therefore the shear force for this location is 6 kilonewtons. Okay, I find the shear force. Now what I'm going to do is now let's draw the cross section. This is our cross section. In fact, it is not symmetric with respect to the horizon, so we need to determine the location of the neutral axis. But before than that, let's define some variables. So let's say that this is t, and I have the width of the flange b, thickness of the flange is also t, and I have the height of the web, and I will say that it is h. So h is given as 0.07 meters, b is given as 0.05 meters, and t is given as 2 centimeters, 0.02 meters. Okay, so these are my dimensions. Now what I'm going to do is I will calculate the location of the neutral axis. Therefore, first I need to choose a reference point for my coordinate. In fact, I can choose arbitrary location. So I will choose this time my reference point as the upper line. For my coordinate system. So this is my y. Now, first I'm going to calculate the location of the neutral axis. In fact, for this purpose, I will divide the whole cross section into two sections. So this will be y1 and a1. So y1 is the centroid, and then I will have this part. So y2 will be the centroid and a2 will be the area of this section, of this region. So now let's calculate the location of the neutral axis. So y bar is equal to y1 a1 plus y2 a2 divided by a1 plus a2. Okay, so y1 is located at h divided by 2. Area is h multiplied by t plus the second area. The second area is located, the centroid is located at h plus t divided by 2, and the area is b multiplied by t. So this is the first moment of the area of the first part, first region. So this one, this region, this area, and this is the first moment of the area of this section or region. Okay, now the total area is h multiplied by t plus b multiplied by t. So if you put the values, what you are going to get is 0.05 375 meters. Okay, now let's calculate the bending moment of inertia with respect to the neutral axis. So this will be our next step. Now we have just found the location of the neutral axis. Now we will calculate the bending moment of inertia of the neutral axis. In fact, first we have this horizontal part, and then the second one, this region, or vice versa, doesn't matter, so both are the same. So 1/12 the width is b, height is t cube. Let's write it a little bit low, sorry. I will rewrite the equation here. It is 1/12 b t cube plus area b times t, and distance to the neutral axis, so that is h plus t minus y bar and the square of this distance plus moment of inertia of the vertical part, that is 1/12 th cube plus, now we will shift the centroid to the neutral axis, that is area t times h multiplied by distance of the centroid to the neutral axis, and that is h divided by 2 minus y bar square. So again, let me repeat it. So the second part has the width of t, h cube plus area multiplied by distance of the centroid of the area to the neutral axis and square of it. Okay, so if you put the values into their places, what you are going to get is 1.0 78 10 to the power minus 6 meter to the power 4. So this is the bending moment of inertia. Now we will calculate the shear stress So remember the shear stress formula. Let me remind you. Tau is equal to shear force multiplied by Q, first moment of the area, divided by bending moment of inertia with respect to the neutral axis, multiplied by the thickness of the actual thickness of thickness at that point. So for us it is T, and this is bending moment of inertia at B, because we are asked for the stress at point B and B on the web. So the thickness of the web is T, and we will calculate the first moment of the area QB. So in fact this means that we will calculate the first moment of this area. So this is QB, so B is here. Okay, let's calculate the QB. QB is the area multiplied by distance to the centroid. So it is B times T, and distance to the centroid is equal to H plus T divided by 2 minus Y bar. So this is the moment of the first moment of the area above point B. If you put the values, what you are going to get for the first moment of the area is 2.625 10 to the power minus 5 meter to the cube. So this is the first moment of the area. In fact, from here we can calculate the shear stress at point B. Shear stress is, again, I will rewrite the formula, V times QB divided by I and A multiplied by T. So V at this point is 6 kilonewtons. It is 6 10 to the power 3. QB is 2.625 10 to the power minus 5. Bending moment of inertia is 1.78 10 to the power minus 6, and thickness is 0.02. And in fact, what you are going to get is 4.424 megapascals as a result. Okay, our question is 725. Determine the maximum shear stress in the T-beam at section C. Show the result on a volume element at this point. So we have a beam which has a T cross-section, T-like cross-section, and we have a distributed load on it, and we are asked for the maximum shear stress at point C. Now, okay, first thing that we need to do is to draw the shear force diagram and determine the shear force at point C. So for this purpose, we will begin by drawing the free body diagram of the system in order to determine the support reactions. Now at point A I have two support reactions. Point A doesn't, it is simply supported there, so FAY and FAX. I just choose the direction of the forces arbitrarily, so I have only reaction force in Y direction at point B, and then I have distributed load. It is uniform up to a point, and then it decreases linearly to B. So point C is somewhere here. So the distance between C and B is, let's say, A. This distance is also A. Sorry for the drawing, it's not proportional. And this distance is, let's say, 2A. And the magnitude of the distributed force is W0. Okay, so these are my this is our beam. In fact, we don't have any force component in the x direction, so if we say that the horizon is aligned with the x and vertical direction is y, so I only have forces in y direction. Therefore, I will say that sum of the forces in y direction is equal to 0. FAX is automatically 0. I will not calculate it. So sum of the forces in y direction is equal to 0. In fact, this is FBY plus FAY plus. Now I need to calculate the resultant force of this uniform part. It is W0 multiplied by 2A Now this linearly decreasing part, the peak magnitude is W0 and the height is 2A. So remember that it's a triangle shaped, therefore I will consider the area under the triangle. It is W0 multiplied by A, and this is equal to 0. Now next thing is some of the moments this will be my first equation. So let's say that this is 1. In fact, let me write the variable a. A is 1.5 meters and W0 is given in the problem. It is 10 kilonewtons per meter. Okay. Now this is my first equation. In fact, I will write the second one. Sum of the moments with respect to any point is 0. I will choose point B for the calculation of the moment. In fact, this will eliminate the force Fby. Therefore, I can choose any direction as positive, it doesn't matter. So clockwise direction, I will consider the clockwise direction as positive. For the moment. So first is the moment of the Fay, multiplied by 4a. Now what I'm going to do is certainly this distributed load has a moment in the counterclockwise direction, and therefore I will put another coordinate system. Let's say that x bar attach to point B and in the opposite direction. So minus, now I will calculate the moment generated by this uniform part. So I will just take some arbitrary distance x and I will just get a tiny slice there, which is the x bar, and then I will integrate it. So I will sum up the moments generated by this distributed load. So the bounds for the integral is from 2a to 4a. Distributed load at any location is W0. Moment arm is x bar. Dx bar. Okay, now I will consider the uniformly decreasing moment of this uniformly decreasing part. So again, it is negative. It is from 0 to 2a. At any location, the moment is W0, sorry, the force is W0 divided by 2a multiplied by x bar multiplied by, and the moment arm is x bar. And this is equal to 0. If you do the integration, what you are going to get is Fay multiplied by 4a. This is minus W0 x bar square divided by 2 from 2a to 4a minus W0 divided by 2a x bar cube divided by 3 and the limits of the integral is from 0 to 2a, and this is equal to 0. Okay. So from here you can calculate the FAY. FAY is equal to 4a. We can put these expressions on the other side of the equality, so this becomes a square minus 4a square divided by 2, and this is minus W0 divided by multiplied by 8 a cube, sorry, a square divided by 6. Now from here you can easily calculate the FAY. FAY is so let's make one correction. This is plus because we put the equation to the other side of the equality, and in fact FAY from here can be found as W0 multiplied by A multiplied by 11 divided by 6. So if you put the values, what you are going to obtain for the value of the FAY is 23.83 kilonewtons. Now in fact you can calculate the FPY. So FPY is equal to, in this case, 7 W0 divided by 6 multiplied by A, and then you will obtain the value of 15.166 kilonewtons. Okay, so these are the forces, support reactions. Now, in fact, we can cut the structure from either side, but this time we are asked for the shear stress at point C, so maximum shear stress for point C. Therefore, I prefer to cut the structure from right hand side, and I will just make one cut and then determine the force. I will directly cut the structure from point C. Instead of obtaining the whole shear force distribution. So this is my point C. Now I have the force Fby here. In fact, I have this linear distribution, and I have the shear force for this cross section. Let's say it is V1, and I have the moment here, M1. So this is point C. Okay, so from here I can easily write the static equilibrium. I don't need to calculate the bending moment. So V1 is equal to, this distance is A, never forget that. This is W0 divided by 2 here. So from geometry you can easily find the magnitude of the maximum distributed load, or magnitude of the distributed load at point C. Since it is uniformly decreasing, I can easily say that it is W0 divided by 2 multiplied by A divided by 2. So it is W0 multiplied by A divided by 4 minus Fby. This is the shear force. If you put the values, what you are going to obtain is minus 11.416 kilonewtons. So minus 11.416 kilonewtons for the shear force at this point. Now we are asked for the maximum shear stress. Okay, now let's draw the cross section. It's a cross section is T. Okay, now let's define the variables for this cross section. I have the thickness of the flange. This is T. This is 0.03 meters. In fact, this is T as well, and again it is 0.03. I have the width B. B is 0.15, and I have the point H. And H is .15 as well. So these are my dimensions. In fact, the cross section is not symmetric. I need to find the neutral axis. So I need to choose a reference point. In fact, I prefer to choose the base bottom of the cross section as my reference. Now I will calculate the location of the neutral axis. So location of the neutral axis is in fact now I will divide the whole cross section into two units. So first I will begin from the vertical part. The centroid of the vertical part is located at h divided by 2 multiplied by its area. It is t times h plus, now the vertical part is the centroid is located at h plus t divided by 2, and area is b multiplied by t. So this is the moment, first moment of the area, which is vertical. So this is the first moment of the web, area of the web, and this is the first moment of the area of the flange. And we will divide it by the total area. Total area is t multiplied by h plus b multiplied by t. So if you put the values, what you are going to get is 0.12 meters. So the neutral axis is located at 0.12 meters away from the bottom of the cross section. Now we need to calculate the bending moment of inertia with respect to the neutral axis. This will be the second step. First, I will write the bending moment of inertia of the vertical part. So the web 1/12 t multiplied by h cube plus t multiplied by h. Now we will shift this to the neutral axis. So t multiplied by h, area multiplied by distance between the centroids. So this is h divided by 2 minus y&a square I will continue below. So now the moment of inertia of the flange, this is 1/12 b t cube plus, now we will shift it again, b times t. Now its centroid is located at h plus t divided by 2 minus y and a, and square of it. So if you put the values, what you are going to get is 2.7 10 to the power minus 5 meter to the power 4. So this is the bending moment of inertia. Now we need to calculate the first moment of the area above the natural axis, because this basically means that we are looking for remember that the shear stress formula. In fact, the bending moment of inertia is constant, and certainly the shear force is constant. Therefore, the shear stress is maximum when Q divided by the width, so is maximum. So in fact, we know that the thickness T is thickness, so the width here on the web it's maximum, and certainly on the neutral axis the area above the neutral axis has the maximum first moment of the area, because the area is getting larger. And in fact, remember that the first moment of the area is moment area multiplied by the distance of the centroid, therefore it's maximum here. So let's calculate the first moment of the area. For the neutral axis. Now there are two regions. First, the first moment of the flange. So the flange has the centroid, the distance of its centroid to the neutral axis is t divided by 2 plus h minus y and a multiplied by the area, it is b times t. I will continue below. Plus, now the small part. So basically now I will calculate the first moment of this region. In fact, it is h minus y and a divided by 2. This is distance to the neutral axis, so distances between the centroids, multiplied by its area, it is H minus Y Na multiplied by T. Now from here we can obtain the Q. It is 2.16 10 to the power minus 4 meter to the cube. Now we can calculate the shear. So maximum shear stress, tau max is equal to V multiplied by Q max divided by INA multiplied by the thickness. In fact, if you put the values, it is minus 3.04 megapascals. So minus comes because of the choice of the direction of the shear stress. So basically this means that if you are drawing a volume element, so it is like this. Shear stress on the volume element is like this. So the directions are like this. Now our question is 733. The beam is constructed from two boards fastened together at the top and bottom with two rows of nails spaced every 150 millimeters. If an internal shear force of V 3 kN is applied to the board, determine the shear force resisted by each nail. Okay, so we have two boards. As a result, we have a rectangular cross section, and it has a height of 100 millimeters and width of 150 millimeters. In fact, this rectangular beam is constructed by application of two nails at every 150 millimeters. Now certainly this vertical force, the shear force, generates a shear at the interface, and this is the location where we see the at this interface. In fact, we can easily say that this is the location where we see the maximum stress. So as a result, this shear stress generates a force in this region. So, and this shear force will be carried by these two nails. So let's make the calculation. First I'm going to define some variables. In fact, I will begin by defining the length. So the distance between two nails as L. This is 0.15 meters. Now the half, so the height of each board is 50 millimeters, so it is 0.05 meters, and the width is B, that is again 0.15 meters. I will calculate the shear force. For this purpose we need to calculate the first moment of the area and bending moment of inertia. So the first moment of the area, so this is NA, so we will calculate the first moment of this area. Certainly this is B and this distance is H. So first moment of the area is H divided by 2 multiplied by B multiplied by H. So it is 0.05 squared divided by 2 multiplied by 0.15, and value is 18.75 10 to the power minus 5 meter to the cube. Now let's calculate the bending moment of inertia. I. So it is 1 over 12 B multiplied by 2H cube. So it is 1 over 12 0.15 multiplied by 0.1 cube of 0.1, and the value that you are going to get is 1.25. Ten to the power minus 5 meter to the power 4. So this is the first moment of the area. It is first moment of the area 18.75 10 to the power minus 5 meter to the cube, and bending moment of inertia is 1.25 10 to the power minus 5 meter to the power 4. Okay, now let's calculate the shear stress at the interface. It is tau is equal to B multiplied by Q divided by I multiplied by B. This is the shear stress. So V is 3000, Q is 18.75 10 to the power minus 5 divided by 1.25 10 to the power minus 5 multiplied by B. B is 0.15, and the value that we have is 0.3 megapascals. Now we need to calculate the force carried by each nail. In fact, if we look at from the side to the interface, this is what we are going to see. So we have V here So certainly the shear force is in this direction. So we have shear force like this at the interface of two boards, and so basically the net force carried by the two nails is then the width, because let's say that this is the distance between two nails, L, so the force is L multiplied by the width, B, multiplied by the shear stress. Since we have two nails, force will be shared by the nails. So we can easily calculate it. So the shear stress is 0.3 10 to the power 6. L is equal to 0.15. B is equal to 0.15 divided by 2. And from there we have the value of 3,375 newtons. Okay, our problem is 737. Three identical boards are bolted together to form the built-up beam. If the wood has an allowable shear stress of T allowable 3 megapascals, determine the maximum allowable internal shear V that can act on the beam. Also find the corresponding average shear stress in 9 mm diameter bolts which are spaced equally at S is equal to 150 millimeters. Okay, so we have a cross section which is non-symmetric with respect to the horizontal axis. So we are asked for the maximum force, allowable shear stress is given, and then we are asked for the average shear stress in the bolts. Okay, so now first thing that we need to do is find the location of the neutral axis, but for this purpose let us first draw the cross section. We have three identical boards. Now, in fact, in order to calculate, first thing, maybe it's better to define some, define the variables, assign the values for them. So, the thickness of each board is, let's say, B. Now, this distance is H. This is also H. And the last one is also H. Now we need to define reference point, so I put my reference point to the bottom of the cross section. So here we need to find the location of the neutral axis. Let's say that it is located at y bar. So location of the neutral axis is basically sum of the moments of the area divided by sum of the area Now we have two identical boards on the left and right hand side, and their centroid is located at a distance of h. Their areas are 2h multiplied by b plus the area of the center part, and its centroid is located at 2h again. Its area is 2h multiplied by b divided by 2 times 2h b plus 2h times b. Well, maybe it's better now to define the variables. H is given as 0.05, B is given as 0.025 meters, and we have the S, the spacing between the bolts, it is 0.15. Now let's return back to y bar. Y bar is located at 0.066 meters. Now we need to calculate first we are asked for the maximum force. So in fact then we can consider that whole cross section is made of perfectly bonded, and therefore we know that the shear stress is, the formula of the shear stress is solely depends on moment of area, first moment of the area divided by the thickness. In fact, this basically means that we see the maximum stress at a point where this ratio is maximum. So the first moment of the area divided by the thickness. In fact, thickness is minimum here, and so the area is larger, therefore the maximum stress can be obtained either at this point or on the neutral axis, and let's say that this point is A. So we will see the maximum stress either at point A or on the neutral axis. This means that we need to calculate the first moment of the area for point A and for neutral axis. So let's do it for point A first. QA. Now, area above this point has a centroid of 5h divided by 2. This is the centroid area above point A, minus y bar, distance to the neutral axis, multiplied by its area. Area is h times b. And the value that we are going to have is 7.3 10 to the power minus 5 meter to the cube. So this is the area. Now let's calculate the first moment of the area with respect to the neutral axis. Now first moment of the area with respect to the neutral axis is, so this is basically area above the neutral axis. Let's make a correction. This is not 7.03, this is 703. 73 10 to the power minus 5 meter to the cube. Okay, now this is our moment of inertia at point A. Now let's calculate the moment of inertia, first moment of the area, with respect to the neutral axis. Now we will consider the area above the neutral axis. So for this purpose we can divide the whole now we will consider the area above the neutral axis. So therefore we can calculate the moment of the areas, first moment of the areas in different ways. So in any case we will sum them up. So either we can calculate the first moment of these areas with respect to the neutral axis and then calculate the upper part, or what we can do is we can calculate the first moment of area above A and then this rectangular region. So this is much more better because this already we calculated. This is QA. So QNA is equal to first moment of the area of this part QA plus this region, and this region has the width of 2h divided by 2h multiplied by y bar. So QNA is equal to QA plus 2h minus y bar divided by 2. This is basically distance to the neutral axis multiplied by the area 2h minus y bar multiplied by 3b. So the result is 1.163 10 to the power minus 4 meter to the cube. Now the point is, okay, this is larger than QA, but the point is we are looking for the Q value divided by the thickness. So in fact at the point of A the thickness is B, so it is 0.025, and at the point of on the neutral axis it is 1.163. So Q divided by the thickness ratio at the neutral axis is much smaller than the value at point A. Therefore, we will see the maximum stress at point A. In fact, this helps us, and therefore we need to calculate the maximum force according to point A. So from the shear stress formula we can easily write that maximum force is equal to allowable shear stress multiplied by the natural axis multiplied by the thickness B. Or let me write the formula better, this will make you confused in fact. So shear stress is equal to Vmax multiplied by QA divided by INA multiplied by the thickness. So this is the expression. In fact, from here we can easily calculate the Vmax. Vmax is equal to T allowable multiplied by INA multiplied by B divided by QA. Now if we put the values, or let's write here, that's better maybe. Vmax maximum shear force can be found as 10,714.3 newtons. So this is the first part of our question. Now we are asked for the average shear stress that's carried by the nuts, sorry, not nuts, bolts. Okay, so now in fact let's say that mainly the force is transmitted through these two interfaces. So and in fact force carried by this center block, so let's say that this is B. Now what we need to do is to integrate the shear through this block. In fact it's nothing more than or in other words we need to calculate the shear flow at the interface, at this interface. So we have two interfaces here, but mainly we have one block at the center, and therefore we can easily calculate the shear flow. For this purpose we need to calculate the first moment of the this area. QB, let's say. QB is equal to area, that is 2h multiplied by b, and distance of this area to the centroid. That is 2h divided by minus y bar. So this is the distance to the centroid, and what you are going to get is, if you put the values, it is 8.33 10 to the power minus 5 meter to the cube. Now we can calculate the shear stress at the interface. So the shear stress at the interface is maximum force, shear force, multiplied by QB divided by INA. This is the shear flow, multiplied by H. Now this has to be equal to force transmitted to the balls. In fact, we have two areas, so this is 2F divided by H times S. So H is the height, that interface, and S is the distance between two balls. From here we can calculate the force that comes to the one volt. So F can be calculated as Vmax multiplied by QB multiplied by distance between the balls, S, divided by INA, and what we are going to get is 6,428.57 newtons. Now we can calculate the shear stress, average shear stress. So basically the average shear stress is the area force divided by the area. This is the force that comes to the bolt. So the average shear stress is equal to force divided by area of the bolt, that is force divided by P d square divided by 4, and force is 6,428.57. P diameter is 9 millimeters, 9 10 to the power minus 3 to the square divided by 4, and what you are going to get is, as a result, .051 megapascals. Okay, our problem is 741. The simply supported beam is built up from 3 boards by nailing them together as shown. If P is equal to 12 kilonewtons, determine the maximum allowable spacing S of the nails to support that load. If each nail can resist a shear force of 1.5 kilonewtons. Okay, so we have a beam. It is simply supported at A and B. The length of the beam is 2 meters. There is a point force at the center, which has a magnitude of 12 kilonewtons. The beam has a I-beam made of wood by nailing 3 pieces of wood. The dimensions of the cross section are given. Anyway, so first thing that we need to do is, of course, we need to determine the shear force distribution. Therefore, we first need to calculate the support reactions at A and B. So let's draw the free body diagram of the system. This is our beam. Okay, so this is point, the left hand side is point A. I have 2 forces at point A, FAY and FAX. I just choose the direction arbitrarily, and then I have force in the y direction, FBY, and I have the point load P. Of course, this means that X is horizontal and Y is vertical. So from static equilibrium, I can easily say that FAX is 0 and FAY is equal to FBY, because the point load is just at the center, and that's equal to P divided by 2. Okay, so of course, let's define the variables associated with the length of the beam. So let's say that this distance is again L, and we have another distance here that is also L, and let's say that L is equal to 1 meters. Okay, now we can begin to cut the structure from either side. In fact, I prefer to cut the structure from left hand side. So this is FAY. I have the shear force, internal shear force, and I have the bending moment at the cut. So I cut the structure from somewhere between point A and the location where I apply the point load. So I will omit the moment. I don't need to calculate it. In fact, so V1 is equal to P divided by 2 from here, obviously. Now I will make the second cut. I will make the second cut somewhere between the point load and point B. This is FAY. This is my force. This is M2. Okay, now certainly again I don't need to calculate the bending moment. I will not calculate it, but we can easily see from here V2 is from static equilibrium. It is minus P divided by 2, because FAY is equal to P, so obviously the result will be minus P divided by 2. So these are the forces, shear forces. Now let's draw the shear force diagram. So I put the origin A and this is B. So it is something like this. So this is P divided by 2 and this is minus P divided by 2, and this is the shear force. So I have minus P divided by 2 between the location where I apply the point load and point B, and it is P divided by 2 between A and the point load. Okay, so these are the forces. Now we need to calculate the shear stress. In order to do that, first let us define the variables. In fact, let us draw the cross section again, cross section of the beam. Now we know the in fact, our beam is made of 3 wooden boards by nailing them. So this shear force, so the magnitude of the shear force is constant everywhere, only the direction changes. So let's define let's assign some variables to the dimensions. So let's say that this is B. This is T. This thickness is T as well. And board to board distance is H. In fact, the cross section is symmetric both horizontally and vertically. This basically means that the neutral, we already know the location of the neutral axis. We don't need to calculate the neutral location of the neutral axis because it's at the center. Now we can calculate the moment of inertia. We can calculate the bending moment of inertia for this cross section, in fact. With respect to the neutral axis. So first, the web of the I-beam. So the center part, vertical part, it is 1/12 T H cube. Now the flanges, so the horizontal part. Now I have two pieces, one at the top and one at the below. So it is 2 1/12 B multiplied by T cube plus B times T, and now distance of its centroid to the neutral axis, so it is H plus T divided by 2. And square of it. So let me repeat it again. So we have 1/12 TH cube, that is the moment of inertia of this vertical part, and I have two pieces which are horizontally aligned. So 1/12 BT cube is the moment of inertia with respect to its center, plus, now I will calculate, transfer the moment of inertia to the neutral axis. In fact, that is plus BT area multiplied by distance to the neutral axis. So H plus T divided by 2 to the square. In fact, we have the dimensions already given. H is 0.2 meters, B is 0.1 meter, and T is 0.025 meters. Now if we put all these values, into this expression, what we are going to get is 8.02 10 to the power minus 5 meter to the power 4. Now certainly what happens is this. So here we have the nail and we have another nail here. Therefore the shear stress, force generated by the shear stress at this interface, is mainly carried by the nail. So what we need to do is we need to calculate the shear stress for this particular location, and therefore we need to calculate the first moment of the area. So we need to calculate the first moment of the area of this part in order to calculate the shear stress at this point. So it is Q. The centroid is located at h plus t divided by 2, and the area is b times t. If we put the values, we have 2.81 10 to the power minus 4, and the unit is meter to the power cube. So this is the first moment of the area. Now we can calculate the shear stress for this particular location. In fact, shear stress that comes to the nail or at the interface is equal to P divided by 2 multiplied by Q divided by INA multiplied by the thickness. Now if we put the values, we already calculate all the values. P is known, that is 12 kilonewtons. Q is known, this is 2.81 10 to the power minus 4. Moment of inertia is 8.02 10 to the power minus 5, and T is equal to 0.025. In fact, from here what you are going to get is 841.55 kilopascals. Now this stress is distributed to the nails. This is the stress at the interface of two boards. Therefore the nails are carrying the total force carried by all the nails is shear stress applied to the interface multiplied by the area. Area is 2L multiplied by the thickness. So the total length of the beam multiplied by the thickness. So this is the force carried by all the nails. From here, if you put the values, what you are going to get is 42.078 kilonewtons. Now we know all the forces. In fact, we know the allowable force that can be resisted by the each nail. In fact, this is the total shear force. So total number of the nails can be calculated from here. F nail divided by force allowable. Now force allowable is given. F nail is 42.78. Force allowable, so allowable force that one nail can carry is 1.5. From here, what we find is 28.5. Therefore, we can say that the total number of nails is 29. So we need 29 nails. Of course, we can calculate the spacing between the nails. So the spacing is let's say S. It is total length divided by total number of nails. So it is basically, for this problem, 2 divided by 29. What you are going to get is 0.0689 for the spacing. Okay, our problem is 742. The T-beam is nailed together as shown. If the nails can each support a shear force of 4.5 kilonewtons, determine the maximum shear force V that the beam can support and the corresponding maximum nail spacing S to the nearest multiples of 5 millimeters. The allowable shear stress for the wood is 3 megapascals. So we have a cross section T-beam made of wood, and it is made by nailing the two pieces together. The dimensions of the T-beam is given. The width is 300 millimeters and the height of the web is 300 millimeters. In fact, the thickness of the board is 50 millimeters, and we are asked for the spacing between the nails, and in fact we are asked for the maximum shear force that can be carried by the beam cross section. So we are given the allowable shear stress as T megapascals, 3 megapascals. Certainly it is the maximum value. Therefore we will compare it by the maximum shear stress, and in fact we know that the maximum shear stress is obtained on the neutral axis. Since the cross section is not symmetric, we first need to determine the location of the neutral axis. So this is what we are going to do, in fact. So let's draw the cross section. This is my cross section. Now let's define the variables. In fact, this is T, the board thickness. I have the H, the height of the web, and this is, let's say, B. In fact, it has a thickness of T. So H is given as 300 millimeters, so it is 0.3 meters. B is given as 0.3 meters, and the thickness is 0.05 meters. Now what we need to do is, first we will calculate the location of the neutral axis. We don't know the location. We choose the reference point, the bottom of the cross section as reference point. So we have two areas. One is at the top, so let's say that this is Y1 and area 1, and we have the other one, this is Y2 and area 2. So the location of the neutral axis is Y1 A1 plus Y2 A2 divided by area 1 plus area 2. So the centroid of the Y1 is located at H plus T over 2. Multiplied by the area. Area is B times T. Plus H divided by 2 is the location of the centroid of the area 2, and the area is H multiplied by T. We will divide it by the total area. It is B times T plus H times T. Okay, so if you put the values, what we are going to get for the location of the neutral axis is 0.22. Now we need to calculate the moment of the first moment of the area, but in fact let's look at the cross section again. Now we can easily say that we will see the maximum, so we need to calculate the shear force, and in order to do that we can easily say that the maximum shear stress will be seen on the neutral axis, because we know that it is maximum for a constant shear force. It is maximum when Q to the ratio of the thickness is maximum. In fact, here the width of the cross section is smaller, and we have the maximum value of the Q on the neutral axis for this particular T-beam. So let's calculate the moment of the area, first moment of the area above the neutral axis. This is what we are going to do. So first moment of the area above the neutral axis is first the horizontal part. The distance between the neutral axis and distance of the centroid of the horizontal part is h plus t divided by 2 minus y na. Multiplied by the area, and the area is b times t plus now centroid of the vertical part. So this is h minus YNA divided by 2 multiplied by h minus YNA multiplied by t. If you put the values, what you're going to get is 1.21 10 to the power minus 3 meter to the cube. Now, of course, this is the Q value for the neutral axis, and in fact we need to know the Q value of this particular location, because this is where we need to calculate the shear stress, because we don't know whether the wood will fail or the nails will fail. So certainly the shear force, we must find the shear force which will satisfy both conditions. Therefore we need to establish a relationship between the allowable force of the nail and maximum shear stress. So we are given the maximum shear stress. Okay, so let's calculate the first moment of the area for this particular location, that is Qn. Q nails. So we will consider the area above the vertical part. It has the centroid at h plus t divided by 2 minus YNA multiplied by B times T. And if we put the values, what you are going to get is 105 10 to the power minus 3 meter to the cube. Okay, now let's, from here we can easily calculate the shear at the interface at that particular location. So let's say that toenail is equal to shear force multiplied by Qn divided by INA multiplied by the thickness. So this is the shear stress at the interface between two boards, and this has to be equal to the force carried by the nails. So remember that each nail can carry a shear force, and certainly this will be distributed to the spacing. So it is the distance between the nails, S is the distance between the nails, and T is the thickness of the board. So Fn is already given to us. So Fn is in the question 4.5 kilonewtons. Now this is our first expression. In fact, from here we can calculate the V. So V can be calculated from here as a function of nail, because we already know the Qn, we know ENA, T, we don't know S only. So let's write the V from here. V is equal to Fn multiplied by INA divided by Qn multiplied by the S. Now let's return back the maximum shear stress formula. This is the V. So remember that tau max is equal to V multiplied by QNA, because we see the maximum shear stress on the natural axis, divided by INA multiplied by the T. Now we know the Fn, so we can substitute Fn into this expression. By the way, this is equal to T allowable in order to structure to withstand. So let's substitute this V into this expression. So what we are going to get is tau allowable is equal to Fn multiplied by INA divided by Qn multiplied by S multiplied by Qna divided by Ina multiplied by ds. So these two will cancel each other, and now we can, in this equality, only unknown is the S, so the spacing, sorry, this is T. Only unknown is the distance between the nails now. So we can calculate the distance between the nails from here. So S is equal to Fn multiplied by Qmax divided by tau L oval shear stress multiplied by Qn multiplied by T. Now we can put the values. So Fn is 4.5 10 to the power 3. Qmax it is the Q neutral axis, Qna, sorry. It is the same thing, so just a correction. In order to be consistent, so it is 1.21 10 to the power minus 3 divided by T L oval. L oval shear stress is 3 megapascals, 3 10 to the power 6. Qn is 1.05 10 to the power minus 3, and T, the thickness is 0.05. So basically S is equal to, if we do these calculations, S is found to be 0.0345, so 34.5 centimeters. Now, in fact, S is wanted to be multiples of 5 millimeters, and therefore if we use a distance of 35 millimeters, this means that the nails will not be able to carry the load because it will exceed their allowable shear stress force. Therefore S is equal to 30 millimeters. So this is the answer of the question.